This is lesson 5.2, interpreting graphs. We have several different ways to represent linear relations. In the last lesson, we talked about table of values and equations. Remember, our equation is y equals ax plus b, where a represents the rate of change and b represents the starting value. We can also represent linear relations by a graph. This would be an example right here. Linear relations are always straight lines when you graph them. So it's really easy to identify them because if it's a perfectly straight line, then it's a linear relation. This is true because linear relations grow by a consistent amount. So if we were to look at our table of values, remember the x's are all going up by the same amount each time, and the y's are all going up by the same amount each time. So when this turns into a graph, you're going up and over by the same amount each time, which creates a straight line. When we're given a graph, we can pick out values from the graph. So we could say, well, when x equals this, what is the corresponding y value for this linear relation? So for example, what is the x value when y equals 3? So that would be right here. When y equals 3, where is the linear relation at? If this was written in a table of values, when y equals 3, what is the corresponding x value? And we can pick this out from the graph. So I've drawn in a dotted blue line my thought process. We start at y equals 3, and we draw a dotted line until we hit the linear relation. And once we do that, we draw a dotted line all the way down until we hit the x-axis. So this shows us that when y equals 3, x also equals 3. For b, we want to find the y value when x is -2. So we start here at x equals -2, and we draw a dotted line until we hit the linear relation. Then we continue that line until we hit the y-axis, which would be at -2. So when x equals -2, y also equals -2. But sometimes it's not always going to work out as nicely as this example. This linear relation goes through the grid lines exactly, so it's really easy to pick out the points. But what if that line doesn't hit the points exactly, which most of the time that's going to be the case? Then all we're going to do is estimate the values as best we can. So in this example here, you can see that the linear relation, it's still a straight line, it's still a linear relation, but it's not always going through the grid lines. There's some points where it goes exactly through it, so those would be easy to find, but not all of them are. So we'll estimate. What is the x value when y equals -4? So we would start right here. That's when y equals -4. Draw our dotted line until we hit the linear relation. From there, continue our line up until we hit the x-axis. And then you can see that it's approximately just past 6. Since this scale is going up by 2, like 7 would be somewhere in the middle, so we can guess that this part right here is about 6.5. For b, we want to find what is the y value when x equals -6. So here's x equals -6, draw the dotted line until we hit the linear relation, and then extend that line across until you hit the y-axis. And then we can approximate that would be about 4.5. This method has a name, it's called interpolation. And this is when we estimate values between ones that we already have. So yeah, we don't have these exact points drawn out already, but they exist somewhere on the graph, and we are doing the best we can to estimate what those values are. We're not given them in advance, but we're using what we're given in the graph to estimate what those values are. It's called interpolation because it's in the information we already have. There's something else called extrapolation. This is when we estimate values outside of what we already have or outside of the graph that exists. So you can remember it by interpolation is estimating from what you already have, and extrapolation is estimating what we don't have. It's extra outside of the graph that we can already see. But both of them are estimating values. So here's an example of extrapolation. In black here, we have our linear relation, but it doesn't continue past what we've already drawn. So you can see three distinct points have been identified, and the line kind of stops right here. And we want to estimate the value of y when x equals 30, which would be all the way out here. So it's not existing on the graph already, so it would not be interpolating what we're doing. We're extrapolating this pattern out, continuing the pattern further past what we already have to estimate what that value might be. So this is a useful skill in all sorts of contexts. So let's say you only have information up to a certain point, but you know what the pattern is. So just continue that pattern to get any of the future data points that you don't already have. If we want to estimate the value of y when x equals 30, we go to x equals 30 here, and we draw our dotted line up. Normally, we draw the dotted line and stop when we hit the linear relation, but we don't really know where the linear relation is because that's what we're estimating. So what I would recommend is getting a ruler out or some straight edge, and if you hold it against your linear relation, you can see how the pattern would continue if it did continue. Because remember, linear relations are always a complete straight line. So when you do that this way, we continue our 30 up, and this part here is what would be continued if we put a ruler against our linear relation, and we get this point here. So if this linear relation continued in the pattern that it already has, then it would be at +6 when x equals 30. So y equals 6 is our guess when x equals 30. It's still an estimate because that data doesn't actually exist, but it's a pretty solid extrapolation. Bringing back what we talked about last lesson, discrete data versus continuous data. So remember, discrete data jumps from point to point and does not include the values in between them. Whereas continuous data is, you can think of it as a smooth, connected group of points where every single value in between counts. What this looks like on a graph is this. So a continuous line or a continuous graph is exactly that. It's a line that continues, all of the points are included. Every single data point on that line is counted. But for discrete, there's no line to connect those points. It's just the individual data points and nothing in between. So it's saying it can only exist here, or here, or here, not in between those values. And it just depends on the context. So a couple more examples. An example of discrete data would be, let's say you're comparing how many shirts you bought versus how much money you spent. So as a table of values, maybe it might look like this, for each shirt you're buying, it's costing you $10 extra. So in this context, the data is discrete because you can't buy half of a shirt or 3/4 of a shirt. This data is discrete, so only these exact points would be graphed. They would not be connected in a straight line. So very briefly, it might look like this. They're not connected, but we have the individual data points on the graph. An example of a continuous one might be time that has passed versus how far you've walked. So we've got time in minutes, it's going up by 10 minutes each time, and then kilometers walked, your distance, going up by 1 each time. So I don't know, approximately 10 minutes to walk a kilometer. Distance and time are always continuous. If you think about it, time is always continuing forward. You can have an entire minute, half of a minute, like every little second counts. Time is continuously occurring. And the same thing with distance. It's not like when you're walking, you either only go 1 kilometer and then you jump right next to 2 kilometers. Unless you're teleporting, you're gonna have all the little bits of distance in between 1 and 2 kilometers. So that's kind of what I wrote out there. So since distance and time are continuous, this data is continuous, and it would be a connected line on the graph. So again, a quick sketch, maybe it would look something like this. Every little piece is included in between. The line is connected because as time moves forward, you move further in the walk that you're doing, and every little piece in between counts. To finish off this lesson, we want to understand movement in a graph. How can we apply context to a linear graph that we are presented with? So in this example, yes, it's split into 6 different segments, but each of those segments, which I've numbered, are linear in of themselves because they're straight lines. And in this particular graph, the x-axis is time passed and the y-axis is distance. So I've put an example here of maybe you're going for a run. How can I interpret what I'm seeing here in the graph? If this is somebody running, how could this be interpreted into a real life story or real life context? So for the first segment here, the graph is quickly going up. It's very steep, and so not much time has passed, but it's jumping way up. So maybe that's you running really fast. you know, you've covered a lot of meters in very short amount of time. So you're running really fast. But then for the second segment there, you're suddenly going in the opposite direction. So for whatever reason, you've turned around and you're running back where you came from. The second segment is a little bit less steep, so you're running a tiny bit slower because you're covering some distance in you're covering the distance in a longer amount of time. In the third segment, it's a completely flat line. So time is going forward, but distance is not changing. So this might be you stopping for a break, let's say. And then the little segment 4, maybe you did a short, tiny sprint. You just sprinted up. And then segment 5, again, you turned around, you're going in the other direction, and you're going for a pretty fast run because this is pretty steep going down. And then the last segment 6, you're continuing where you were going, but now it's not very steep. So maybe this is an easy jog the rest of the way home. So of course, everybody could interpret this different. This is just one example, but the main idea I'm trying to get across is how to look at linear relations and look at graphs and understand how that could apply in a real life context. So if the line is really steep, maybe it's moving very quickly. If the line is completely flat, then nothing is changing. You're stopped somewhere. And depending on the direction, if you're going up or down, that also depends on the direction that you're maybe running or swimming or whatever the context is. So in this lesson, we talked about interpreting different graphs, comparing discrete and continuous data, interpolation versus extrapolation, and essentially being able to just identify different values from a graph.